Today we'll discuss a theory of perturbation for degenerate levels, and I'll represent you only some approach to this theory. And I can tell that the application of perturbation theory to generate systems can often lead to powerful insights into the physics of the system considered. This is because the reason of this is that perturbation leaves the degeneracy of the energy levels. And let's imagine that we have some Hamiltonian acting on the U wave function and in the following form, and it has some energy spectra, energy n, U wave function n, and I have some perturbation that is connected with some unperturbed Hamiltonian plus beta and the perturbation. It's some common theory of perturbation, but I will explain how it's applied for the degenerate case of levels. Previously I discussed the case of non-degenerate levels. And we have here Hamiltonian, and we can rewrite the energy of the system in the following form: energy n equals some based initial energy that corresponds to the unperturbed Hamiltonian, or for the case of non-degenerate case of levels, or not for the case of unperturbed Hamiltonian plus the first approximation of this energy plus beta squared, second approximation, and plus some nodes. I'm very lazy to write it to the infinity, and I can tell again, as mentioned by the law, that the first corrections are enough for our built-up theory. Oh, excuse me, this is not equals here, plus beta. And it's, I will explain why we write in the following form this perturbation theory, because we will collect members and we will take here the energy and state here. This wave function we take here instead, we'll collect members by the same powers of beta. And let's make this operation again. I explain you that I repeated this case of but it seems to me it could be enough useful for you to repeat it again, because the quantum mechanics is enough interesting. And plus plus plus, which equals energy 0n plus beta energy first approximation and 0n plus beta first approximation. This expression should be enough for us. Okay, since I'll repeat it on plus 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 something, and close the bracket. And now let's start. Let's rewrite. Let's collect terms by beginning by 0 power of beta, and we can collect it h0 and multiplication 0 and function, and plus energy 1 plus equals energy 1 and 0 1 function. The first power gives us the following form: h apostrophe and its multiplication of 0 1 function plus h0 with its multiplication and first correction to the wave function, and it's all equals energy 0n. and plus energy M0. Energy 1, 0, and function. And here I want to say stop, and let's write it. Stop. I have given you some usual theory of perturbation, and you have the question: where is the main difference? Where is this degeneracy? How could I include this degeneracy to this theory? And the answer is very simple. Not so simple. Let's imagine. What does mean the degeneracy? The degeneracy. The degenerate structure of levels. Okay, I have given here some structure of levels, and several of these levels have some energy. Energy 0, 1, 0 approximation, 0, 2. And this energy for different levels. This sign that defines the number of level, and this is the sign of approximation. So if you'll see here, see that this is the approximation of a function, this degree of approximation, and this is the number of target level or target wave function. And for example, for every of this level, in the case of degenerate wave functions, we have only single wave function. But for example, for this level, we will have two wave function, 0, 1 and 0, 2, and that's why it means that for the same energy, the Hamiltonian, there are two wave functions that, or more than one, for the same energy level. And some outside perturbation can reach this degeneracy, and that's why this theory is enough important. But in comparison to the previously one theory, we have two wave functions, same energy. And you have the question, what's the difference? We can write for every energy such equation. And the answer will be following. Let's write for these two wave functions this equation. I'll take n and make it equals to, for example, it's 2 and 3. n2 and n3. And maybe you have a piece of question, what practical issue does it have, the theory of perturbation for the general case? For the practical issue, of course, I'll tell it further, that we'll consider the case of perturbed theory near this degree of degeneracy. And let's write only for this case I'll take attention 0, 2. I'll take n that equals 2 and write it here. Plus H0 energy first approximation and second level. Energy first, second. Energy 0, 2 plus energy 0, 2. And first approximation wave function. And let's write the same equation, for example, for the following form. 0, 3 plus H 0, 1, 3, that equals energy 3, 0, 3 plus energy 0, 2, energy 3. We have two equations for two different numbers. And let's take, for example, some set of and represent the set of first wave function, first approximation of the wave function as the set of unperturbed wave function for this Hamiltonian, and I'll write it in the following form. And coefficient. And this theory of perturbation is based on such representation. And let's rewrite the first equation then, for example. 0n, 0k, and let's write it. But before we'll apply this relation, I'll take this equation, for example, and take energy from the right side to the left one, and rewrite this equation in such way. For example, H apostrophe minus energy 2, 0 to wave function, and it's all equals. I'll take this term and I'll take it here. Energy 0 2 minus energy 0, and now I will explain you why this degeneracy is enough. Is to be impossible to consider from the usual point of view of theory of perturbation for the degenerate case, and I'll show it now. Then we take that energy 1 2 equals k energy 2k 0k, and I'll take this relation and state here. Then I'll rewrite this expression in the following form: energy 2 0 2 that equals the summation of the a to k energy 0 2 minus energy 0k. I have applied this Hamiltonian to this wave function after the substitution of this to this place. For example, I have applied it on every wave function. If I apply a Hamiltonian on this wave function, I'll take the constant and this wave function. It's the common rule of quantum mechanics. I hope it's enough clear for me. For example, it means that we will write H key equals O key 0 key wave function. And that's why I'll take it here. It's on my constant coefficients that are not influenced by the Hamiltonian. That's why I have this formal relation. And let's imagine that I multiply both sides on the 0 free wave function. Why I have used this wave function is the wave function that has the same energy level as this wave function, for example. And let's multiply from the right side on this wave function. And we will gain the following case: H 3 2 minus J this wave function are orthogonal to each other. That's why these terms goes to 0, and this all equals to the following member: A to k 0 2 minus 0 3, because this set of wave functions is orthonormal, and I have the following relation: and I'll write that from this condition that A to 3 equals H apostrophe and this difference. I'll of course write that the rule of orthonormality of this wave function after the multiplication and integration all over the space. 0 2 dv 0 3 equals delta 2 3 is delta function, that equals in our case to the 0. And I have represented the following constant coefficient in the following case. But we remember that this level is degenerate and we have two-way function for the same set of energy level. That's why energy 0, 2 equals energy 0, 3. And it means that this coefficient comes to 0 because this is 0. We have the following relation H apostrophe on the 0. We have the infinity, which means that theory of perturbation doesn't work because the sum of the terms adds the limits to the infinity, and the theory of perturbation doesn't work at all. And you have the question, what we can do here? We can't apply the theory. And I have represented this example not only from the point of view of our interest. I have shown that if you have the degenerate case of level, we have some other conditions and some problems in comparison to the usual theory of perturbation, because we have the problem of infinity of some coefficient regarding this particular level. And this problem can be lifted with the following quantum mechanical rule. We can represent some wave function, and it will be some basic initial wave function that can be a linear combination of the wave function for the degenerate level, for example 0, 2, V0, C1 first, C2, 0, 3. And we will write some theory, but in this case we will not have two wave functions 0, 2, 0, 3, and some problems regarding the infinity constant coefficients of within such relations. Yes, we will have only single wave functions connected to these two functions, and that's why if we will write this set of wave functions 0, 1, 0, 2, 0, 3, 0, 4, etc. I'll take two wave functions and tell that we can take the influence with the help of only single wave function, and that's when the common theory will be built up only for the following set of wave function. And that's why it will be very similar to the usual theory of perturbation. And that's why in this case I will have to rewrite this equation mentioned in this form, that we have two equations, yes, as the sum of this equation. And let's write it now. Ctrl C, Ctrl V, and write sum of these equations. And these equations can be given as following: H apostrophe minus some energy one with multiplication to this wave function with 0, 2 plus C2 with 0, 3, and the all equals to the sum K A to K, energy 0, 2 minus energy 0, K, and the set of such wave function that are orthonormal. And in this case, multiply both sides on the and we can multiply it on the conjugated wave function, complex conjugated wave function, integrate all over the space. As was mentioned here, we have multiplied on the energy conjugated wave function. And we will take some matrix from which we can identify these coefficients C1 and C2 mentioned below. Let's realize this multiplication. This multiplication follows to the following. Equation apostrophe 2 minus energy 1 C1 plus C2 H apostrophe 2 3. I'll remember that it all equals to 0, and if we'll multiply both sides on this wave function, I'll have the following equation: H apostrophe 3 3 minus energy 1 C2 plus C1 H apostrophe 3 2. So equals to 0. And why how I get this equation? For example, I multiply it here, and so I can realize it. If I multiply it, for this term, it will converge to 0, because for every energy that equals to 0, as mentioned, that equals to energy 2, for the kind that equals to the energy 2, this converges to 0, but for the other cases, this wave function are orthonormal, as in the usual theory of perturbation, and I can build up some matrix using this that can help us to solve this equation. H apostrophe 2 3 H apostrophe 3 2 H apostrophe 3 3 minus energy 1, and it's all equals to 0. The solution of this determinant follows to two energy first values, substituting this into this equation. This equation gives us some C1, C2 coefficients, and thus we have found as a result we have two values. We have two sets of C1 and C2, and as a result we have identified has found two zero wave functions 0 1 and 0 2 that align combinations of C1 energy 1 plus C2 U2. And for this wave function we have C1 energy 1 plus C2 energy 2, and which in general correspond to different first order correction to the energy of perturbation. Hence, as we expected, one of the perturbation may be removed with the degeneracy. And in the final form follows us to the solution of the problem of infinite terms that can be written from the theory after the convergence of this unit to 0. And this is only some common representations. Further, I'll give you much more practical applications of the theory of perturbation for degenerate levels, or some levels that are near degeneracy. Thanks for your attention. I hope this theory was very useful. Be very happy.